Why does GPT-4 process 128,000 tokens, while the original transformer choked on just 512? The answer lies in how attention is computed. In this video, we'll explore 5 attention mechanisms. From the original multi-head attention to flash attention. Let's start from the beginning. Multi-head attention was introduced in the original transformer paper in 2017. The core idea is simple. Instead of one attention calculation, we split it into multiple parallel heads. Each head has its own query, key, and value projections. This allows the model to attend to different aspects of the input simultaneously. One head might look at syntax, another at semantics, another at position. After processing, all heads are concatenated and projected back. The benefit? MHA captures diverse relationships in the data. But there's a problem. During generation, we need to cache keys and values for every head. This KV cache grows linearly with sequence length and number of heads. For large models with long contexts, memory becomes the bottleneck. Enter multi-query attention, or MQA. The key insight: what if all heads shared the same keys and values? Each head still has its own query projection. They all look at the same K and V. This dramatically reduces the KV cache size. Models like Palm and Falcon use MQA for faster inference. But sharing everything can hurt model quality. That's where grouped query attention comes in. GQA is the middle ground. Instead of one shared KV pair or one per head, we group heads and share KV within each group. Llama 2 and Mistral use 8 KV heads for 32 query heads. This gives near MQA speed with near MHA quality. Think of it as a spectrum. MHA on one end, MQA on the other, GQA in between. Now let's talk about long sequences. Standard attention has ON2 complexity. Every token attends to every other token. For 100K tokens, that's 10 billion attention computations. Sliding window attention solves this by limiting the view. Each token only attends to a fixed window of neighbors. A typical window size is 4096 tokens. This reduces complexity from ON2 to ONXW. But wait, doesn't that lose global context? Here's the clever part. With multiple layers, information propagates outward. Layer 1 sees 4K tokens, Layer 2 effectively sees 8K, and so on. Mistral combines sliding window with GQA for efficient long context models. All the methods we've discussed change the attention algorithm. Flash attention is different. It optimizes how we compute attention on GPUs. GPUs have 2 types of memory. HBM is large but slow. SRAM is tiny but fast. Standard attention writes intermediate results to HBM repeatedly. Flash attention rewrites the algorithm to minimize memory transfers. It loads Q, K, V in tiles, computes attention in SRAM, and writes back once. The math is identical, the result is exact, but it's 3 to 5 times faster. Flash attention works with any attention type. MHA, MQA, GQA. It's why 128K context windows are now practical. Let's put it all together. Multi-head attention, best quality, highest memory usage. Multi-query attention, fastest but may sacrifice quality. Grouped query attention, the sweet spot for modern LLMs. Sliding window enables long sequences with local context. Flash attention makes everything faster on GPU hardware. In practice, modern models combine these techniques. Llama 2 uses GQA, Mistral uses GQA plus sliding window. And almost everyone uses flash attention under the hood. If you want to learn more, check the links in the description. Thanks for watching.